Swayam Prabha. Digital India. Educated India.
Today we will continue our discussion on dynamics of second order systems, and we will start today with a physical example of non-interacting system. Example of the non-interacting system. It was told that if two first order systems or two first order tanks are connected in series, the overall response is second order response. So, today we will take that example. I mean, two first order systems, those are first order tank systems connected in series. So, this is tank 1. Input to this tank is Fi. Cross sectional area is A1 and height is H1. Output is F1 and resistance to flow is suppose R1. This outlet from tank 1 enters tank 2. This is tank 2. Cross sectional area of this tank 2 is A2 and liquid height in the tank is H2. Output stream from tank 2 is F2 and suppose this resistance is R2. This is the example of a non-interacting system. Now, what are the modeling equations for these two tanks? If we consider tank 1, the modeling equation is A1 dH1 dt equals input flow rate, that is Fi, minus output flow rate, that is R1. This is the modeling equation for tank 1. Now, F1 is again we can write by this form H1 divided by R1. F1 equals H1 divided by R1. driving force divided by resistance to flow. If we substitute this F1 equals H1 divided by R1 in the modeling equation, then we have A1 dH1 dt equals Fi minus H1 divided by R1. Substituting the expression of F1, we finally get this. Rearranging this equation, we have A1 dH1 dt plus H1 divided by R1 equals Fi. Fine. Rearranging, we get this. Now, if we write this equation in terms of deviation variables, then we obtain A1 dH1 prime dt plus H1 prime divided by R1 equals Fi prime. This is the modeling equation in terms of deviation variables. Fine. Now, if we multiply both sides by R1, then we get A1 R1 dH1 prime dt plus H1 prime equals R1 Fi prime. This equation we get by multiplying both sides with R1. Fine. Now, we will assume that A1 R1 equals tau P1 and R1 is equal to Kp1. We assume A1 R1 equals tau P1, which is time constant for the first tank, and R1 equals Kp1. This is the gain of the first tank. Then the equation, modeling equation becomes tau P1 dH1 prime dt plus H1 prime equal to, this is Kp1 Fi prime. This is the first order differential equation of the output H1. Now, if we take Laplace transform and rearrange, then we get the transfer function of the first tank as H1 bar prime S divided by Fi bar prime S equals Kp1 divided by tau P1 S plus 1. This is the transfer function of the first tank. That is tank 1. Now, we will represent this as Z1 S. Similarly, we will consider tank 2. Similarly, we will consider tank 2. For tank 2, we can write the modeling equation as A2 dH2 dt equals input flow rate, that is F1, minus output flow rate, that is F2. Now, F2 is again the driving force divided by resistance to flow. So, F2 equal to H2 divided by R2. If we substitute that in this modeling equation, we get A2 dH2 dt equal to F1 minus H2 divided by R2. Multiplying both sides by R2 and rearranging, we get A2 R2 dH2 dt plus H2 equal to R2 multiplied by F1. Fine. Multiplying both sides by resistance R2 and rearranging, we get this equation. Now, similarly, we have to represent this equation in terms of deviation variables. Then we get A2 R2 dH2 prime dt plus H2 prime equal to R2 F1 prime. This is represented in terms of deviation variables. Fine. Now, we assume A2 R2 equals tau P2 and R2 is equal to Kp2. We assume A2 R2 is equal to the time constant for tank 2 and R2 as gain of the tank 2. Then we get tau P2 dH2 prime dt plus H2 prime equal to Kp2 F1 prime, and taking Laplace transform, finally we get the transfer function of tank 2 as Z2s equals H2 bar prime s divided by F1 bar prime s equals Kp2 divided by tau P2s plus 1. This is the transfer function of the second tank, that is tank 2. This is the transfer function of the second tank. Now, if you see the schematic of the two tank system, we can say that the overall transfer function will be H2 bar prime s divided by Fi bar prime s. Fine. The overall transfer function of this two tank system can be written Z naught s equals H2 bar prime s, this is the output of tank 2, divided by the input to tank 1. Fine. This is the overall transfer function. Now, we can write again the overall transfer function by this form: H2 bar prime S divided by F1 bar prime S multiplied by F1 bar prime S divided by Fi bar prime S. Can we write this? The overall transfer function we can write in this form. So, this is equal to H2 bar prime S divided by F1 bar prime S. This is nothing but the transfer function of tank 2. And what is F1 bar prime S? We know F1 bar equals H1 bar divided by R1. For the tank 1, we have considered this correlation: F1 bar equals H1 bar divided by R1. That means H1 bar divided by Kp1. Can we write this? Now, this relationship we will substitute here. I mean, F1 bar, F1 prime, this is not bar, sorry, prime, F1 prime equals H1 prime divided by Kp1. So, if we substitute here H1 bar prime S divided by Kp1 Fi bar prime S. Can we write this? There is no change of this term. Now, in place of F1 prime, we have substituted H1 prime divided by Kp1, and then Fi prime remains there. So, the first term, this one, represents Gp2, not Gp2, that is Z2, and multiplied by this, which is Z1 divided by Kp1. That means Kp2 divided by tau P2S plus 1 multiplied by 1 divided by Kp1 multiplied by Kp1 divided by tau P1S plus 1. Agree? So, the overall transfer function G naught S we can write as Kp2 divided by tau P1S plus 1 multiplied by tau P2S plus 1. This is the overall transfer function of the example non-interacting system. So, G naught S is basically H2 bar prime S divided by Fi bar prime S. We can write in this form. Now, we will introduce a unit step change in the input variable. Considering a unit step change in Fi and taking inverse of Laplace transform, we get the output in time domain as H2 prime t equals Kp2 1 plus 1 divided by tau P2 minus tau P1 tau p1 exponential of minus t divided by tau p1 minus tau p2 exponential of minus t divided by tau p2. Considering a unit step change in f I bar prime s, I mean f I bar prime s equals 1 by s, and taking inverse of Laplace transform, we get the expression of output H2 in time domain like this. Fine. Now we will conclude based on this discussion. So, first conclusion is that by connecting two first order systems in series, we get overall second order dynamics. Fine. By connecting two first order systems in series, we obtain second order dynamics. So, by connecting two first order systems in series, the overall dynamics becomes second order dynamics. This is the first conclusion. Second thing is, we wish to observe the behavior making a plot. So, this is H2 prime t divided by Kp2 versus time. The steady state is represented by the dotted line, and the dynamics is like this. This is for first order system. This is the dynamics of first order system. This is the dynamics of second order or two non-interacting tanks system, and this is the dynamics of four non-interacting tanks. Four non-interacting tanks. Fine. For the first order system, this should be H by Kp. For two non-interacting tanks, this should be H2 divided by Kp2 or H2 prime by Kp2. For four non-interacting tanks, this should be H4 prime t divided by Kp4. So, this is the dynamic behavior of three systems. Now, what conclusion we can make? Initially, you see it changes slowly. For the two non-interacting tank system, initially it changes slowly, then it picks up the speed. The behavior for second and higher order systems is S-shaped. Fine. The behavior is S-shaped. So, initially it changes slowly, then it picks up the speed. Fine. So, this is basically the overdamped response. And third conclusion is, as the number of capacities in series increases, the delay in the initial response becomes more pronounced. You see, if you compare these two curves, the delay is more for the case of 4 non-interacting tank systems. So, that is the third conclusion. As the number of capacities in series increases, the delay in the initial response becomes more pronounced. This is the third conclusion. Fine. So, this is the example, physical example of a non-interacting tanks system. In the next, we will consider an interacting tank system. We will connect two tanks in series so that they are interactive to each other. So, next example is the example of the interacting system. Fine. For the case of interacting system, similarly we will consider two tanks which are connected in series. This is tank 1, cross sectional area of A1 and H1. Input is Fi, resistance to flow is R1, this is tank 2, cross sectional area A2, height is H2, this flow rate is F1, and the stream which is coming out from tank 2 has the flow rate of F2 and resistance is R2. So, the modeling equation for tank 1 we can write in this form: A1 dH1 dt equals Fi minus F1. What is F1 here? What is the relationship of F1? F1 equals H1 minus H2 divided by R1. Since H1 is higher than H2, that is why there is a flow. So, if we substitute this, then we obtain A1 R1 dH1 dt plus H1 minus H2 equals R1 Fi. If we substitute the expression of F1 in the modeling equation, then we get this equation. Similarly, for tank 2, the modeling equation we can write in this form: A2 dH2 dt plus H2 divided by R2 equals H1 minus H2 divided by R1. Can we write this for tank 2? A2 dH2 dt plus F2 equal to F1. Fine. Now, these two modeling equations we need to write in terms of deviation variables. Anyway, before that we can rearrange this equation and we obtain A2 R2 dH2 dt plus 1 plus R2 divided by R1 H2 minus R2 divided by R1 H1 equal to 0. By rearranging the modeling equation for tank 2, finally we get this equation. Fine. Now we wish to write these two equations in terms of deviation variables. So for tank 1 we can write the modeling equation in terms of deviation variables and we obtain A1 R1 dH1 prime dt plus H1 prime minus H2 prime equals R1 Fi prime. This is for tank 1. Similarly, for tank 2 we can write the modeling equation in terms of deviation variables as A2 R2 dH2 prime dt plus 1 plus R2 divided by R1 H2 prime minus R2 divided by R1 H1 prime equals 0. This is for tank 2. Fine. Now we will take Laplace transform of these two equations. Taking Laplace transform, we get for tank 1 A1 R1 S plus 1 H1 bar prime S minus H2 bar prime S equals R1 Fi bar prime S. Taking Laplace transform for the case of tank 1, I mean the modeling equation of tank 1, we obtain this form. Similarly, if we take the Laplace transform of this, we obtain minus R2 divided by R1 H1 bar prime S plus A2 R2 S plus 1 plus R2 divided by R1 H2 bar prime S equals 0. If we take the Laplace transform for the modeling equation of tank 2, we obtain this expression. Now we need to solve these two equations to obtain the transfer function with respect to tank 1 as well as tank 2. Solving these two equations, we get the transfer function for tank 1 as H1 bar prime S equals tau P2 R1 S plus R1 plus R2 divided by tau P1 tau P2 S square plus tau P1 plus tau P2 plus A1 R2 multiplied by S plus 1 F I bar prime S. This is for tank 1. Fine. Solving these two equations, we obtain the transfer function for tank 1 in this form. Similarly, for tank 2, we obtain the transfer function as H2 bar prime S equals R2 divided by tau P1 tau P2 A square plus tau P1 plus tau P2 plus A1 R2 S plus 1 Fi bar prime S. This is the transfer function with respect to H2. Fine. So, can we say that this is the representation of overall transfer function? Because overall transfer function we can represent by H2 bar prime S divided by Fi bar prime S. So, this overall transfer function we obtain for the case of interacting system. Interacting system. This overall transfer function we obtain for the case of interacting system. What is the overall transfer function of the non-interacting system? For the non-interacting system, we obtained the overall transfer function in this form Kp2 divided by tau P1 S plus 1 multiplied by tau P2 S plus 1, just we obtained before this discussion. So, we can write this as R2 divided by tau P1 tau P2 S square plus tau P1 plus tau P2 S plus 1, sorry, it will be multiplied with Fi bar prime S. So, Fi bar prime S. This is the overall transfer function for non-interacting system. Can you compare these two overall transfer functions? If we compare, we see that one extra term is there for the case of interacting system, that is U1 R2. This term, this is the additional term which is present in the overall transfer function of interacting tank system. So, this term may be thought of as the interaction factor. This term A1 R2 may be thought of as the interaction factor. Fine. If we compare the two transfer functions, we see that one additional term A1 R2 is present in the overall transfer function of interacting system, and this term may be thought of as the interaction factor. Now, we will conclude based on this discussion for the case of interacting system. What is the first conclusion? First conclusion is that the overall response is second order response. This is the first conclusion. By connecting two first order liquid tanks in series, we obtain the overall response as second order response. So, the overall response is second order response. Second conclusion, in the second conclusion we wish to first find the roots. What are the roots? There are two roots, because if you see the denominator, that is a second order polynomial, that is a quadratic, that is given in quadratic form. So, the roots we can write in this form: tau p1 plus tau p2 plus a1 r2 plus minus root over tau p1 plus tau p2 plus a1 r2 whole square minus 4 tau p1 tau p2 divided by 2 tau p1 tau p2. Fine. There are two roots and they are represented by this form. Now, tau p1 plus tau p2 plus a1 r2 whole square minus 4 tau p1 tau p2 is greater than 0. Fine. That means two distinct real poles. So, what about the overall response? The overall response is overdamped response. So, we obtain zeta greater than 1, and the response of interacting capacities is always overdamped. The response of interacting capacities is always overdamped. So, these are about the two tank systems. I mean, we observe that if two first order systems are connected in series, the overall response is second order response. Another case we mentioned in the previous class, that second order system we can obtain by employing one controller around a process. We mentioned three cases. One is by connecting two first order systems in series, one is by employing one controller with a process, and in the third case we considered that few systems are inherently higher order systems. So, now we will consider the process having a controller. We wish to observe the higher order dynamics, I mean second order dynamics, for the case of a first order process configured with a controller. If a controller is employed for a first order process, what will be the overall dynamics that we wish to observe? So, we will first consider one example, that is the liquid tank system. This is a liquid tank system. Inlet flow rate is Fi and outlet flow rate is F naught. This is height, cross sectional area is A. control objective is to maintain the height of the liquid in the tank. So, for that we need to employ one level controller. So, our control objective is to maintain the height of liquid in the tank, that means the control variable is H and the corresponding manipulated variable is F naught. Fine. This is the control pair for this case. Now, what is the modeling equation? Modeling equation in terms of deviation variables we can write as A dH prime dt equals F I prime minus F naught prime. Fine. Now, since the controller is manipulating F naught, so we can correlate F naught with the height by a controller equation. Suppose the controller equation is given as F naught equals F naught S plus Kc H prime plus Kc divided by tau y integration of H prime dt plus Kc tau d dH prime dt. This is the equation of a controller which we will discuss in the subsequent classes. Fine. This is the controller equation which is correlating the manipulated variable F naught with height. H prime is H minus Hs. Fine. Now, we can write this equation as F naught prime equals Kc H prime plus Kc divided by tau y integration H prime dt plus Kc tau d dH prime dt, where F naught prime equals F naught minus F naught S. And in this equation Kc, tau y and tau d, these three are controller tuning parameters. In this controller equation Kc, tau y and tau d are constant parameters. Fine. Now, we can substitute the expression of F naught prime in the modeling equation. By substituting the expression of F naught prime in the modeling equation, we obtain A dH prime dt plus Kc H prime plus Kc divided by tau y integration H prime dt plus Kc tau d dH prime dt equals F I prime. Substituting the expression of F naught prime in the modeling equation, we obtain this. Now, taking Laplace transform, we get A plus Kc tau d is H bar prime S plus Kc H bar prime S plus Kc divided by tau I S H bar prime S equals Fi bar prime S. Fine. Taking Laplace transform, we obtain this. So, we can write this as tau I divided by Kc A plus Kc tau d S square H bar prime S plus tau I S H bar prime S plus H bar prime S equals tau I S divided by Kc Fi bar prime S. Now, we can represent this as tau square S square H bar prime S plus 2 zeta tau S H bar prime S plus H bar prime S equals Kp multiplied by S Fi bar prime S. Fine. So, the transfer function can be represented by H bar prime S divided by Fi bar prime S equals Kps divided by tau square S square plus 2 zeta tau S plus 1. The transfer function yields this form: H bar prime S divided by Fi bar prime S equals Kps divided by tau square S square plus 2 zeta tau S plus 1. Now, here Kp is equal to tau I divided by Kc. Similarly, tau square is equal to tau I divided by Kc A plus Kc tau d, and 2 zeta tau is equal to tau I. Fine. We have considered in the derivation of transfer function these simplified forms. I mean, these correlations have been used in the derivation of transfer function. So, from these equations we obtain zeta equals half root over of Kc tau I divided by A plus Kc tau d. Fine. This expression for zeta we obtain from these two forms. Now, we want to conclude. So, our first conclusion is that by employing a controller around a first order system, we obtain overall second order response. This is our first conclusion. By employing a controller around a first order system, we obtain overall second order system. And in the second conclusion, we want to know whether it is overdamped or critically damped or underdamped response. If root over of Kc tau I divided by A plus Kc tau d less than 2, then zeta is less than 1. that means this is underdamped response. If this is equal to 2, that means zeta is equal to 1. So, it is critically damped. Fine. Similarly, if this is greater than 2, then zeta is greater than 1, then it is the case of overdamped response. Fine. So, our first conclusion is the overall response becomes second order, and it may be overdamped, may be underdamped, may be critically damped depending on the value of this zeta. Thank you.